Okay. Okay. Oh, okay. So hello everyone. My name is Lo, and our topic is face recognition for facial images. Okay. And our innovation starts from we observed the conventional method and found that the conventional method often composed of two systems, including the reconstruction system and the classification system. Okay. So the separated block often leads to local optimal. So we want to unify the process into a end-to-end training method and thus lead to global optimal. Okay. And we identify the challenge we identify two challenges. And the first challenge is for the model training itself. We found that the feature of the model is hard to converge and thus lead to poor performance. Another challenge is the task itself. We found that due to the fisheye images and the random projection, the distortion is often serious and dynamic. Okay, so to conquer these two challenges, we perform two separated features to solve the problem. The first one is the structural correction. We found that the conventional loss, including the arc phase loss and the cross entropy loss, often focus on the interclass loss. They focus on pushing different classes of feature away and do not focus on gathering or clustering the same class feature. Okay, so our method is to provide an anchor and tell the model or guide the model to learn the feature of the same classes to converge towards the anchor, and thus making the same class of the feature clustering. Okay. And the second method is the spatial transformer network. Okay. This method is to overcome the distortion of the fisheye images. And so by inserting several layers of spatial transformer networks, the feature can be graduated, corrected, and therefore can overcome the distortion of fisheye images. Okay. So the result is shown right here. We can see that with the aid of our two methods, the performance is the red line here. Okay. We can see that the accuracy is near the optimal bound. As for the conventional method, we can see that in the severe distortion, the degradation is very harsh. Okay, so this results in the poor accuracy performance. Here we can see that the conventional method has a huge accuracy degradation. As for our proposed method, we can see that the performance is nearly optimal bound. Okay, so the conclusion is that with our end-to-end method, we can see that the conventional method do not support the end-to-end optimization. As for our method, we support end-to-end optimization and therefore can have a better accuracy. Okay, and that's the end of my talk. Thank you.
I use taxonomy because I work with species identification. So I have taxonomy because like real taxonomy.
Thank you.
That's why there's kind of paths you can use overall. That's a problem. No hard feelings. You can all the time.
So the mic is over.
Okay.
We want the best
So this is the taxonomy-driven learning for semantic hierarchy of classes. So I'm not author of the paper, but I am presenting on behalf of them. So the main work is improving the performance of HSD CNN. So here we train the VGG16 pre-trained model on CIFAR 10 and CIFAR 100 data sets, and by using this taxonomy-driven loss function. So this is actually mainly cross entropy loss with some taxonomy-driven weightage. So these weights, the soft weights, are calculated by using this equation where the distance between A and C, so is the D. Suppose we want to calculate the weight for class C, and D A comma C is the distance between class C and class A. So suppose here this is the class C and this is the class A, so distance will become 2. Like this we calculate weight for soft level weights for the class C, and those weights are used to calculate the cross entropy loss. So after training we use the HSD CNN to divide the features of the network for each node of this node of the clusters, and so this is the output of the quality of clusters, where we can see that in the leaf node one cluster is airplane and ship, so both are similar objects, and second one is automobile and truck, bird and frog, cat and dog, like this way, and this is the results for CIFAR 100. And also that after performing formation of HSD CNN work, we fine tune the network by using 2 different ways. So those are the 2 different results of fine tuning, and we can also see that by performing HSD CNN on the trained model, it improves, it reduces the trainable parameters, and the performance remains almost same.
So when you see one semantic structure of something which is better, it's a lot easier to identify. Theoretically, yes. That is deep learning at its finest. Honestly, we were very surprised that it was close to the numbers we accept as a story on efficiency. We actually outperformed it, which right? Like if you think of how a human being identifies one person, it starts with localizing parts of the face and working from there. Whereas this network is then optimize which one of the semantic features are most relevant to your identification.
You might maybe have like a small meeting in the morning
Oh, okay. Yeah, can you get a video or picture? Yeah, video, picture, whatever. One of the Okay. So, and it's about three minutes, you said?
Yeah.
Okay. Time. Would you like? Okay. Okay. Okay, so look in the camera. Okay. Hi, my name is Lawrence Amadi. I'm with the Illinois Institute of Technology, and today I'll be presenting my work on boosting the performance of weakly supervised 3D human pose estimators using with post-prior regularizers. Now, the theme here is that 3D pose estimation or 3D pose models, data sets are very limited in variety. So usually you have these data sets that have just 5 subjects performing 15 or so actions in a confined space, right? And you train a neural network on this data set, and they do very, very well. But you take it to the real world, and they don't perform as well, right? And the question then becomes, how do we improve the performance of 3D pose estimation for real world scenarios? Now, one way you can do that is to generate synthetic data, which you quickly run into the issue of not having realistic data sets, right? The second approach is what we try to do here, is to take advantage of the abundance of unlabeled video data that are on YouTube or on TikTok or on Instagram, to, that have more variety of persons performing different actions to improve pose estimation. And how we do that really is we try to extract and infuse biomechanical constraints of the human body in our model, right? So what we do is we come up with this semi-supervised pipeline where we jointly optimize a pose model on both unlabeled and labeled data. So for the labeled data, we have input 2D poses, and we pass that through the pose model, which predicts the 3D pose. And then we also pass that through a trajectory model, which predicts the position of a person in 3D space, right? And we optimize both models with the ground truth 3D poses and the ground truth locations, right? Now, this is for the labeled or the fully supervised pipeline. For the unsupervised pipeline, or I like to call it the self-supervised pipeline, what we do is we pass the 2D poses through the pose model and also through the trajectory model. And we predict both the 3D pose and the position of the person, right? Now, we take those two information combined with the camera intrinsic parameters, we can project the 3D pose back to 2D space. And then we compute an L2 loss between the input 2D poses and the projected 2D poses. So effectively what we are doing is we are optimizing the 3D pose model indirectly. Now, not just that, what we then go ahead to do is we find a way to further optimize the 3D pose by constraining it to biomechanical properties. For example, we compute the bone symmetric error, which basically evaluates the similarity between symmetric joints. So for example, the right arm and the left arm should be about the same length, right? So by computing the mean absolute error between symmetric bones, we optimize the bone symmetric constraints, right? Then the second constraint is the bone proportion constraints. And the intuition here is that regardless of the size and the height of a person, we expect certain proportions. So for example, I expect the right arm to have a certain proportion to your leg, right? And by looking at the distribution of the proportions through the labeled poses, we can come up with this very defined probability density function that tells you the likelihood of a bone ratio, right? So then in our network, using this probability density function, you can then compute, given any bone ratio, the likelihood of that ratio, right? And we then optimize we maximize the log likelihood of the bone proportion constraints. Now, for the joint mobility constraint, we apply another biomechanical reasoning here, which is that given any joint, we expect a certain range of motion. So for example, your elbow should go between 0 degrees to 180 degrees, right? Your elbow can't bend backwards, that's impossible, right? So I may not know what the actual pose is, but I know what the pose shouldn't look like, right? And what we do is we find a way to extract the true orientation of each joint that is both scale translation and rotation invariant, right? And this gives us a very fine point cloud of what the orientation, or what the plausible orientations of each joint is, right? So basically, in this graph here, the brighter the color, the more likely that orientation is. So then in our network, we maximize the log likelihood of each orientation, right? So we found that by infusing these biomechanical constraints directly to our pose model, we were able to significantly decrease the error rate for the state-of-the-art network. So we don't you can take literally any pose estimation model and train it using this semi-supervised technique, and you would gain significant decrease in the error rate. And that is in fact what we do. So just to recap, we find a way to infuse biomechanical constraints of human poses into our pose model, and by so doing, we're able to learn from unlabeled video data. And that is really what we do here. So, thank you. How was that? Cool? How many minutes was that?
No, it was really good.
It was good?
So it's good, you presented well. I feel
nice, awesome. Is there a record I can see? Okay. Yeah. Okay. Awesome. All right. Thank you. I appreciate it.
That's well established. Where you'll see any algorithm breakdown is extreme petty, like a yaw pitch of like 40. It doesn't matter which one you take. We're doing this on camera, or just microphone. Different scope.
In your pocket. Okay. Let me know when you're ready. Hello, my name is Ali Hassani. I am a PhD student at the University of Michigan, and I am here to present you a novel application of learning facial structure tasks for identification purposes, where we are actually doing a multitask learning with knowledge distillation. So our problem statement boils down to how can you determine who the person is under noisy conditions. For example, someone's face may be rotated. You might have extreme head pose due to yaw and pitch. They might have an occlusion, an accessory, a cell phone against their face. They may have changed their appearance, facial hair on and off. All of these things are real world scenarios, or even poor illumination. You can almost barely see the person in that image over there. So our question was, why is it that a human being can discern these people, but a deep learning algorithm may not necessarily be able to do so? And we thought about it, we understand what a face looks like. Intuitively, I can go and look at someone and understand these are eyes, a nose, a mouth, and so on and so forth. That has been assumed to be implicitly known when it comes to deep learning, but now we are explicitly teaching it in the form of a multitask learning application. So what we have is an identification task that is jointly learned with a semantic segmentation task. We call this a teaching process. This task right here will teach our network what the face should look like for semantic features, but we don't actually use it for inference. We only use it for a joint learning application. Once all these features are properly encoded down here, you can see the blue for the semantic segmentation is now in the encoder. We actually remove it. And the reason why we remove it is we believe we have all the relevant parameters that are encoded here now in our deep neural network. You may ask, what is the utility of this? Well, on this data set, which has only 67 people, but they're very noisy. Again, 12,000 images that have high variance across within the class. If we take a base network by itself, so a mobile net, it overfits. If you're interested, you can see the validation loss down there, but the test accuracy on the data set is approximately 22%, which shows it's a hard problem. Using a more sophisticated network topology like a ResNet, VGG, or Inception does improve performance. Where we think we have a home run is we actually got near perfect accuracy on the test data set
with 1/10 of the inference parameters. And that is this distillation process at work. There are 6.5 million parameters that are used during training. We can learn exactly what a face looks like. If you consider the UNet architecture, the output of this is literally a semantic segmentation map, and then we can go and optimize that to understand what segmentation map differences are from person to person and get excellent performance on testing. Our next steps on here are to repeat this evaluation on a larger data set. We're currently in the process of label faces in the wild with a semantic segmentation map, and we're going to reevaluate it with a larger amount of people. Thank you so much, and I'm excited for anyone who wants to contact me. My name again is Ali Hassani at the University of Michigan. Well, thank you.
There's a really good presentation. Thank you. You know, it's funny. I'm so tired of looking at the type of thing there. I'm defending my PhD. Yes, next week. Let's do it.
So, yeah, I don't know what what it was, but I know what. For example, right? So I can right? So ideally, but more or less.
Thank you. So, okay. Yeah, of course. Very helpful. Can I start? Hi everyone, I am Antonio Montanaro from Politecnico di Torino in Italy, and I want to present eGLASS, that stands for Explore GAN Lattice Space Solution for Linear Inverse Problem. So we start from a linear inverse problem that is based on the original signal, a forward operator that degrades the image and the noise, and we get an observation. What we want to do is finding a solution that, for example, have higher resolution for super resolution problem, or for in painting some masked observation, and we want to induce a new solution. So we use GAN inversion for finding a solution based on this optimization problem, that is an optimization over the latent space of a GAN, generative adversarial network, and once we have a solution, we propose eGLASS to find any other more solutions. The problem with GAN inversion is that it is a non-convex optimization problem, and there is no feasible guarantee to have natural solutions, and also the computational time. So how we can find the new solutions starting from one solution? This is our proposed method, eGLASS, and we define two Hessians that are the second derivatives of two distances. One is the distance in the induced semantic distance of the image, that is the perceptual distance in the images, and the second one is the measured distance, what we optimize in the GAN inversion problem. So what we want is that we want to find a subspace of solutions where the LP-IPS, that is the semantic distance, is maximized, while the measured distance is low as possible. So we compute the eigenvectors of two Hessians, and then studied the eigenspectrum of the Hessians. It turns out that the eigenvectors encode just the top 10 eigenvectors encode all the semantic difference in the images, while the bottom eigenvectors create a kind of null space where you navigate, but there are no changes in the images. So what we want to do is, starting from a top eigenvector of the induced semantic distance, and try to find out new solution. So, and this is what we do here. And you see, this is our observation. This is the first solution, and these are all the other solutions. There are a lot of semantic changes, but these are not solutions for the inverse problem, because the measured distance, the measurement error is too high. So we propose this kind of orthogonal projection that starts from this eigenvector, the eigenvector of the semantic distance, and project this eigenvector on the null space of the measurement distance. And what we come up is that we found new solutions that are semantically different each other, but still these are solutions because have a low measured distance. So in particular, you can see here how the background of these images change, but these are not related to our solution or to the semantic difference in the images. Indeed, when we apply glass, we find that the background is fixed and the model focuses more on the semantic change of the dog. Then we gain an order of magnitude in terms of time, because if you want to find 100 solutions, for example, for standard method, you need to run 100 times this, and it is a lot in terms of computational time. While applying this kind of projection is immediately obvious, and we gain an order of magnitude in terms of computational time. We apply this method for inpainting of masked faces, for example, for an application on the mask faces during the COVID to solve the impending problem, and we apply it to PG GAN, that is a high resolution image. So that's all. Thank you. Where I can find this video?
And so a lot of times people talk about how important learn what a face is. We've done that explicitly. We said, hey, literally learn what the semantic structure of a face is. And that's the multi-task.
Okay, so it's not on the
So
website.
looking, distillation, it's such a harder task. And the bias of the law
more or less, if it take longer, no problem.
Can I take a few minutes to think about what I'm going to say? Okay. Yeah, I'm ready. No, go. Okay. Hi. Can you hear me? Yeah. Hi, my name is Yi Fan. I'm from Oppo. I'm glad to present our paper on fusion temporal color constancy. So here we propose a framework that combines neural networks, such as convolutional neural networks, recurrent neural networks, and classical color constancy methods into a framework that address the task of temporal color constancy. So there are several advantages to our framework. Number one is modular. You can replace each module in the framework with different kinds of algorithms. Also, it's flexible. We can accommodate single frame and multi-frame inputs. We have a simple interface where you can just input linear raw images and output the predicted illuminant vector. So we have tested our method on several benchmarks, including temporal benchmarks and single frame benchmarks, and we achieve state-of-the-art results on these benchmarks. Something interesting that we found in our studies is that in scenarios like these with skewed color statistics and scenes with few visual cues, the fusion method tends to work better than only classical method or only neural networks. So yeah, that's all. Thank you.
That's perfect, thank you.
C'est bon?
Hi everyone. The idea of this study is to evaluate the object detection performance against distortion in uncontrolled environments. So for this, we designed some new type of of distortion which are locally produced on the image, and the idea is to determine which is the impact of distortion on the state-of-the-art object detection methods, as you can see, with an increased level of severity of the distortion. And the idea, as you can see, when you perform data augmentation with this distorted data set, we improve the robustness of object detection methods by 31.5% for the Euro V4 Chini models. And it's an interesting approach to visualize what is the impact of distortion on the object detection performance for real environments. So at the end, we provide all the source generation code on our GitHub page to produce this distortion, and as well as our distorted COCO dataset. At the end, we perform manual selection of the natural distortion present on the validation set of the COCO dataset. And thanks to it, in the future, researchers will be able to evaluate their models against some natural distortion present on the COCO dataset. So that's it. Sorry. Sorry.
More or less no problem. More or less no problem. And then it's a live version for the persons that are online.
I can try, but I do not guarantee of the quality.
No problem. We've seen I wish I had a shy than you and that went well, so I have no question for you. Okay.
Oui. Je laisse faire. Enfin, j'enlève, je laisse. Et du coup, je stresse maintenant. Oh merde. I start? Okay. Hi, so my name is Olivier. I'm one of the authors of this paper, Fine-Tune Your Classifier, finding some correlation with temperature. So I don't know if all of you have heard about the temperature. The temperature is an hyperparameter which can be used in several ways in machine learning. For example, it was been used with successful applications such as in knowledge distillation, recalibrating neural network, for example, for sampling for text generation. In our case, we are just interested in a particular case, which is classification. How the temperature can affect your classification, and how can we try to predict in advance this hyperparameter. So here, the temperature is this little term, alpha, which is a simple constant, which will you multiply your value before passing through the softmax with. So the idea, let's just jump here before. It's that when you are doing that and learning with a cross-entropy loss, we'll have some issue. If you use the Adam optimizer, Adam is just perfect, so there is no issue at all. But if you want to use, for example, the AGD algorithm optimizer, you have some issue. You can see in the green stuff here that, in fact, there is some drop in performance when you are increasing temperature. Why? In fact, if you take a look at the gradient associated to the cross-entropy loss, you can see that the temperature appears at two places. The first one is here, yes, of course, because the softmax distribution is here, and we use the temperature here. But because of the chain rule, we have the alpha here. And this alpha will have some acting like a second learning rate. It's like if you, in your step of stochastic gradient descent, you multiply by the learning rate and again by the temperature. So obviously, when you augment the temperature, performance decreases because it leads to some divergence. So by dividing the cross-entropy loss by the constant value, you can correct it and have a better results. So you can up to double your results or divide by 2. At least on this specific dataset, it was the things datasets, little dataset of image classification. Here, I will explain more in detail. We are focused on the temperature on the case of the linear classification, just to have a better look and a starting point for the research. So in our case, we have the features which are L2 normalized, and we have the weights of our linear classifier which are L2 normalized. And for now, we are trying to see, we saw that choosing the good hyperparameter will lead to a better performance. So we want to predict in advance, or trying to predict, or getting some intuition of what should be the range of the temperature, in fact. So here we propose a simple pipeline and trying to observe some stuff. So the idea is we take, for example, 12 datasets from MNIST, ImageNet, stuff like that, and we took 9 feature extractors. And by combining all those feature extractors with all the datasets, we are producing some new dataset of embeddings. So we are focused on those embeddings. So we have something like 100 datasets of embeddings. And from those dataset embeddings, we have an issue. How to today those datasets when they are too dissimilar from each other? Because, for example, NIST has 10 classes, this one has 1,000 classes. The number of dimensionality with AlexNet 256 classes, here 2,000 classes is too complex. So we propose to project all the datasets of embeddings into a shared common representational space by computing some statistics. So by saying my dataset has 10 dimension, the separability between classes is that or that or that, etc. You can have this shared common space of representation. So this will be our X, our input data to our regression model, which will try to predict the temperature. So we need to create the Y now, and to create the best optimal temperature, we need to observe it. So for each dataset, we try every temperature with a step of 5 from 1 to 250, and run it for 1,000 epochs, and just observe what was the best accuracy you can reach during those epochs and with which hyperparameter. So when we know that with this temperature we can reach this best accuracy, you have your Y, truc à prédire, stuff to predict. And now you can compute some correlation with all those data statistics and the best temperature we observed here. So we can see those are the most important one, and we have some linear regression which try to predict in advance this temperature. Here we have found some interesting correlation, but correlation is still not causation, so we need to still investigate a bit more. And maybe we think that here we did with a linear correlation, but this work could be interestingly extended by using some non-linear regression, but by using explainable models, because as it would be useless to better understand. So this will be extended. It's a future paper already on archive. The title is something like what can we learn by predicting accuracy? But there is the big picture. I hope I was clear enough. I'm not so sure, but we'll see. Thank you. Bon, pas trop catastrophique? Merci.
Il y a juste ce truc tout comme beurre. Ah non, c'est... Non, l'anglais est assez compliqué et là ça fait au moins 3 ou 4 fois c'est alors c'est un peu drôle, on verra bien. Ouais, ça, en fait, et c'est pour ça qu'en fait il faut qu'on le dégage. Parce qu'en fait, si tu là, parce qu'en fait, tu peux avoir deux trucs optimisés. La température et l'heure de night. Alors que si tu peux avoir de l'heure de night, c'est vrai que ça c'était pas clair, je l'ai pas dit. Ah ouais, d'accord. Ouais, c'est les aléas quand même. Sur les dates, slide of the presentation of the panel. So would you like to present your table? I think the slide.
Yeah, I can take my phone out. It's probably easier. Can you hear me okay? Okay, perfect. So my work is supervising remote sensing change detection models with 3D surface semantics. This is a joint work with my advisor, Dr. Payman Naji-Farad at the University of Texas, San Antonio, in San Antonio, Texas. So essentially, the biggest issue we have in remote sensing right now for change detection, the change detection task is that pretty much everyone uses just ImageNet pre-training, but we actually want to focus on a pre-training method that isn't ImageNet is mostly focused on color and texture, and we want to focus more on features that are relevant to height and surfaces. Since change detection data sets are mostly focused on detecting the difference in surfaces between pre and post images. So what we essentially do is we take a data set which has pairs of RGB and above ground level maps or digital surface models, and we use a normalized temperature cross entropy loss. So we use contrastive learning to essentially pre-train 2 resonant encoders, an image and a DSM encoder. And what we want to do is we actually want to make the feature space very similar between the two. And by iteratively pre-training, we end up with a image encoder that extracts feature relevant height features that are relevant to these downstream tasks. So this first part of our framework, which we call contrasted surface image pre-training, this is the pre-training portion where we have these pairs of images and AGL maps. We pre-train them, and then we take our pre-trained resonant encoder. So we don't do anything with the surface model encoder. We take the image encoder and we use that as the encoder for a UNet model. And then we take this UNet and we fine-tune it on these downstream tasks. So we have 4 data sets which we fine-tune on. So these 3 right here are the change detection data sets. So first we have the OSCD building change detection data set. This uses Sentinel-2 10-meter low-resolution satellite imagery. Then we have the XBD dataset, or the XView2 challenge dataset. This uses Worldview 3 30-centimeter imagery, and this has taken images before and after natural disasters. So we're essentially trying to detect and segment out the buildings that have been demolished due to natural disasters. Then we have the S2 looking dataset, which is more of a rural building change detection data set. This one has labels for both newly built and demolished buildings. And then lastly, we also compared to a data set that's not related to change detection, which is just simple land cover segmentation. So we're focusing on segmenting out grass versus roads versus water. And so essentially through our experiments, we show that our pre-training, our contrasted surface image pre-training works better as pre-training compared to ImageNet when you use it as pre-trained weights of a UNet for these change detection data sets. And then for the land cover data set, it actually performs, ImageNet outperforms us by a small amount. And this also supports our hypothesis that the features that are extracted using our pre-training method are more relevant to height and surfaces, whereas land cover ImageNet, where it focuses more on texture and color, is probably the better choice. All of our code and pre-trained models checkpoints are uploaded to my GitHub that you can access on the link. And so definitely reach out if you have any questions. But that's pretty much it.
Justement, je voulais vous appeler aussi.
Hein? Ouais. 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 Elle est dans le bureau? Ok.
Dans le noir, il y a un sac noir au sol. Would you like to present your work?
En fait, ce qu'il y a, c'est quand on a préparation de l'article, j'ai déjà.
Non, déjà, je vais refuser. C'est que pendant la présentation, en fait, pour le processus d'exposition, j'ai fait un plaster, des diapos, j'ai recevoir de la session poster virtuelle. Et en fait, j'ai envoyé un mail aux organisateurs à la part j'ai l'impression d'avoir fait 4 fois le même travail.
Vous voulez du coup faire l'aide ou pas?
Ça me fait refuser, mais avec le sourire.
Oui, ça me donne plaisir.
Un travail que j'ai déjà fait.
Merci beaucoup. Je reviens pas.
Oh, okay. How can I?
Just put this. Thank you.
Oh, is that okay? Okay, so this work is about object detection in 360-degree image. So the 360-degree image is a spherical image that contains the entire view, and a normal 2D format for this spherical image is equirectangular projection, the ERP. So the ERP is like the Earth, how the Earth projects to a world map. So for the world map, you will see the polar region is highly distorted, and that problem is also happen in the 360-degree image that make the object detection harder. So we propose the dual ERP, which is original ERP with a complementary view. The complementary view is actually rotate the polar region to the center of the image. So we will use the two images for the object detection and make the distorted part recognizable. And for the training and inference, we propose some strategy for this kind of representation. For training, we propose we will use the dual ERP with latitude weighted loss, and the latitude weighted loss will make the detector to focus on the center part, only the center part of the ERP. And for the inference, we will we will have two sets of predictions from each view and then merge them together by filter out the polar region, because there is a lower confidence. So here's the ablation study for training parameter and the inference strategy. And here is the comparison for different type of representation, such as a cube map and a single ERP. And here we can see the DERP, which is our proposed method, show the best result. And for because it can be integrated with different type of detector, we also did some experiment, and the result shows that using dual ERP can improve on different type of detector. And here is some visualization example, and you can see for some hard example that here is a person on a polar region. We can hard to see even by our eyes, but we can detect this human from the dual ERP. That's all about this work. Thank you.
Just my name?
University as well as
Just a minute.
A lot of people back.
Hello, my name is Amit Hennig from Tel Aviv University. We'll be talking now about our research. So usually when training a neural network, you have a lot of access resources. For example, when you train on a big server and afterwards deploy the network to a mobile phone. We would like to utilize those access resources in order to improve our network's performance, specifically considering supervised learning setting. A few words on linear overparameterization or deep linear networks. It has been shown that a deep linear network may have advantages over a single kernel, which is surprising since both share the same computational power. The idea was to introduce these linear cascades to nonlinear networks. So, for example, one may change the kernel while training with a deep linear network, training with it, and when after training, one can calculate the effective convolution, the effective kernel, which will give the same output for the same input. The problem is that for big, deep, nonlinear networks, introducing these kind of linear cascades make the network more vulnerable to vanishing grading problems, and can even harm performance instead of improving it. For that, we introduce our kernel filtering to help prevent the network from becoming unnecessarily deeper. What we do is take the linear cascade and reshape it such that the first kernel is used as the input to the rest of the linear cascade. This generates a filter which is actually the equivalent filter to the whole linear cascade. So with our method, the input signal that propagates does not know that about the access weights. After training is complete, all the access weights can be discarded, and so you are left with the original kernel you wanted. In general, our method, KFLO, kernel filtering linear overparameterization, can be applied to a whole network by creating this linear overparameterization for every filtering layer, such as convolutions or fully connected, training with it, and after training, discarding all of the excess weights where you're left with the original architecture that was desired. Another advantage of our kernel filtering is a reduction in the number of calculations used during training, since usually the input signal is significantly larger than a kernel. We tested our theory on several architectures, comparing to normal vanilla training, exponential moving average, AceNet and DuConv, which are both methods in structural reparameterization, where you create your final network parameters by transforming the parameters of another architecture.
We tested on CFAR 10 and CFAR 100, and we saw that for the architecture we used, we got the highest accuracy. Moreover, we think our framework can be also utilized to other problem settings such as domain adaptation or semi-supervised or incremental learning. In general, a kernel transforming from channel in to channel out has channel out filters. Every filter is alone responsible for a single channel in the output signal. With our method, the generated kernel, each of its filters is in fact a linear combination of the first kernel all the filters in the first kernel in the cascade, weighted by the corresponding filters in the rest of the cascade. This gives us an opportunity to initialize the first kernel with different weights and filters from pre-trained networks and try to apply it to the different problem settings. And I think that's it. Thank you very much.
This is the skill normalized.
Thank you.
Hello.
Okay. All right. Yeah. No problem. Okay.
So the mic is already on. You can present yourself.
Okay, immediately. All right. You give me a sign when I'm talking too long. Okay.
I know, no problem. You can adjust the sound.
Okay.
Does it work?
Da kann man einfach Sachen mit Differenz vorgestellt einreichen und da halt nochmal vorstellen.
Welcome. Thanks for having us. My colleague Philipp Rösch and me. We work on bridge damage recognition. We implemented a Python API called Building Inspection Toolkit. The abbreviation is BIKIT. And via this toolkit, we offer open source data and also pre-trained models, as well as metrics to evaluate the performance of our models. Open source, so the data is easily accessible, and so are the models. Maybe first of all, the quick motivation behind of it. Many bridges were built between 1964 and 1985, and they are in somehow not a satisfying condition, as so to say. So there are many defects occurring on the bridges, and it's why we have to frequently inspect this important infrastructure. And currently the inspections, at least in Germany, only work visually and analog. So it works somehow, the inspector arrives at the bridge and he brings a sketch. Usually the sketch is sketched by hand, and he marks each damage that he recognizes while he's walking along the bridge on the sketch. And we want to simplify that process, and one part of this process that we want to simplify is the classification of the defects. So there are many defects that can occur on bridges. There can be cracks, there can be spalling, there can be efflorescence or exposed rebars, as well as corrosion on the rebars. And until last year, there were only multi-class datasets and binary datasets for this domain. And we tried to, first of all, use that data and get the most out of it and make this data available. So that's why we tried to train models in order to have strong baselines for these data sets, especially for the two data sets called CodePrim and MCDS, which are available in a multi-class data set, and we changed them to a, at least MCDS, we had to change it first to a multi-label setting because first it was only in a multi-class setting available. So what we did was we analyzed 3 different CNN architectures, which are called ResNet 50, MobileNet version 3 large, and EfficientNet version 1 B0. And we used 3 different transfer learning approaches to train the models. First one is called HO, head parameters only. That means we only train the head, not the base or the body of the model of the CNN. And we also analyzed the HTA transfer laning approach, which means head parameters, then all. So we train first the head, the linear layers at the end of our neural network, and then the whole network with a smaller learning rate. And then we also have the third and last approach, which is called DHB, which means different learning rate for head and base. So we only have one training process, and we train the model in one process with different learning rates for the base and the head. And we also did a heavy hyperparameter search, and we analyzed the hidden layer, we analyzed the batch size, we analyzed learning rate, the scheduler, the dropout probability, as well as the optimizer weight decay. And the results are shown here in this table. So we had the best performance for ResNet 50 on the CodePrim dataset with the HTA approach, and it's around 74 EMR, which is the exact match ratio. I will explain that immediately. And we had the best performance on MCDS dataset with the MobileNet version 3 network using the HTA approach as well. The EMR, as you can see, is our main metric to describe the performance of our models on the multi-label data. And EMR means that we have the ratio of exact matches divided by the amount of samples in the test data set. And an exact match is that, or means that each class that is appearing or not appearing on an image is correctly classified. So there's nothing missing or nothing classified too much, so to say. For example, if I have an image with spalling, exposed reinforcement and corrosion, and my model only classifies the spalling and the exposed reinforcement, but misses the corrosion, this classification is not an exact match, so it's not taken into account for this metric. So it's a kind of hard metric. And we also analyze the class-wise recall, which shows us the performance of the model on the specific damage classes, which is also very important, especially from an engineer's point of view, because from the engineer's point of view, it is important to, or they prefer that there are too many defects recognized than to not enough. You know, this is quite worse for the engineer. We also try to, apart from making the data and models easily available, we also provide a separate website called DucklyAI, which displays a leaderboard where you can immediately see which model currently performs best on the specific data sets. So Bikit is the component which makes the data and model easily accessible and also provides the metrics, while DucklyAI is the one showing the leaderboard and shows or somehow fires the competition in this domain. And that's how we try to maximize the velocity of advancements in this domain. Thank you very much for listening.
Okay, is he taking video of me now?
Yeah, no. He's coming.
Okay. All right, hello. I'm Zoshi Pan from National University of Singapore. I'm presenting my work called Speaker Extraction with Cold Speech Gestures Queue. So I first would like to introduce the task of speaker extraction. Speaker extraction extracts only the target speech from a mixture speech that consists of the target speech, interference speech, and other noise. So since this is a mixture speech, there are maybe 2 or 3 speakers. We don't know which speaker it is that we are going to extract. So we need some auxiliary cue to identify who is the speaker we want to extract. So here I'm using gestures cue. So the reason why I use gestures cue is because comparing to lips, it is we don't need that high resolution of lips, and it's not easily being occluded. For example, sometimes people wearing masks, or if they turn their head away, their lips are missing. So in this work, since gestures are highly correlated with our speech content and prosody, we want to explore whether we can use gestures to do speaker extraction. So it turns out, yes, we can do that. So we propose 2 methods. The first one is called SCG network. By just giving the gesture sequence, which are actually the 3D coordinates of 10 spine-centered joints, we can, by concatenating the gestures with the speech features, we can directly do speech extraction. So another method is that we want to do speech separation first, where we first separate the speech in the mixtures into individual clean streams, and we use gesture to define which of the speech is the target speech. So the 2 methods are, no one have done the speech extraction with gesture cue, so we are the first one doing that. Both methods achieve very good performance as long as we correctly get the target speaker. And actually the accuracy of getting the correct speaker in the mixture is really high. It's about 86%. And once we get the correct speaker, the speech signal quality is really high. Yeah, there's a demo here. If you are interested, you can scan the QR code. Yeah, thank you. That's all.
Thank you very much.
Thank you.
Thank you very much. Now is your turn. So, you can first. Okay, if you just and the pockets. All the
So I'm Shumin. I'm from Monash University, Malaysia. So I have a work here is about microexpression classifications, and what we are doing is that we're trying to use the facial action units to label the graph so that we can have the graph for each of these samples, so that and we'll pass it to GCN layers to classify it. So the basic idea is that we are using the facial action units defined by the facts. So all these action units are actually facial muscles descriptions, where they describe some of the muscles movements. For example, we have the brows raising, and also whether our lips are raised because we are smiling and stuff like that. So the idea here is that we are going to pinpoint each of these action units and to refer back to the data set itself to see whether these action units, they co-occurred in the samples or not. So what happens is that if the data set itself says that action units 1, which is the brows, they are triggered when an expression is happening. So they will be considered as labeled as connected in our algorithm here. So the main part of our algorithms, we have adjacency matrix and also feature extractions, where we use a 3D CNN to extract the time series features from the samples. So for the adjacency matrix here, it will be showing the connections between all the action units, and here all these action units, we are treating them as a node in our graph. And if we will be referring to the data set itself, if two or more of these action units, they co-occurred in the data sets, in the samples, they will be labeled as one in the adjacency matrix. So eventually, when we come here, this adjacency matrix will be labeling whether these nodes, they are connected or not. So let's say if in reality, we don't have this much nodes connected, because this is microexpressions. And microexpression is very subtle, so that you might only see like 1 or 2 points are triggered because this is microexpressions. So we might have just 1 or 2 points being connected in our graph. So this graph, whether they are connected, are decided by this adjacency matrix. And at the same time, we will have the input sequence to be passed into our StyNet to extract the 3D features. And these 3D features, it will help us to extract the spatial temporal features. And at the end, we will have to reshape them into dimensions that can be perfectly describing our nodes for each of these nodes. So each of these nodes, let's say for Casimir-2, for example, one of the data sets we are using, let's say we have 19 nodes, which means that we are looking at 19 points of the facial muscle movement. So for each of these points, we will have to extract the features from the StyNet, where we propose it is a 3D CNN structures based on the P3D pseudo-ResNet structure. So we will be reconstructing them so that we have each of these nodes have dimensions of we have here 64, so regardless of what is the dimension, as long as each of these nodes have the same dimensions and each of these nodes have a features, then it can be fit into our AU relation graph. And eventually, this graph, we will be passing them into our AU graph module, which we have our GCN layer and also graph stage to aggregate our features so that we can have more cogent spatial temporal features. And lastly, we'll be classify our graph, which we obtained from the previous layers. And so the results will be, for example, we have 7 class or 8 class for the data sets itself. So we are actually using the graph we construct by the facial action units to classify whether it's a disgust or happy or sad, for example. So yeah, these are the results that we get, and we can actually get some improvement. So the baseline we have is like 50% and 40%, but the one we get is 70%, and so on. So yeah, that's the basic idea of it. Thank you.
Thank you very much.
Okay.
Thank you very much. Je pose juste un je veux juste vous demander une dernière question.
Where's from my friend about his I think so I'm going to at the live of the ICIP 2022, I'm doing a live for the participant that couldn't unfortunately come here. So we'd like you to present your work like in 3 minutes, more or less.
In 3 minutes, okay.
But if it's more or less, no problem.
I see. So I will assume that the audience, those that choose to watch, understand the problem.
Yeah,
right. Okay.
You can measure, you can be more detailed or not, because it's more for the scientific like audience also, like because it's the ICIP participants, it's not public for everyone. So yeah.
Would you like to do it?
You do it.
Oh, is that how it's going to work?
Yeah.
Okay. Are you sure you don't want to do it?
I don't want to do it.
It's good exposure.
No, not for me.
Most of the participants
Have you checked the work of them? He's the first author.
so can we as you are experiencing
a review
Should we take off the back? No problem, right?
Okay.
You have a bright, dark, bright. It's maybe from the beginning you just want to choose. And the problem is the frame rate 30. And then you need to generate also 30 frame rate.
Okay. So I start talking now? Okay, sure, thanks. This paper is basically about person re-identification. So I will assume that the audience understands the basic task of person re-identification. In standard evaluation for re-identification, we don't usually consider which cameras the query or the gallery samples come from, and our work examines that aspect. And what we found was that the performance can be quite different when you use a particular camera, a query from a particular camera, or if the gallery sample is from a particular camera. So what that means is that, for example, if a query comes from camera 1, it may tend to perform better than if it came from camera 2. And conversely, if a gallery sample comes from camera 1, it may be easier to retrieve than that from camera 2. So this kind of imbalance is what we are trying to address in this paper. So one of the obvious causes for this imbalance will be the imbalance of data. Some cameras just capture more images than others because of the way cameras are laid out in an environment. But our paper is not about this, because the obvious solution for that is to just collect more data for the cameras that have less data. But what we examine as well is different cameras have certain biases in terms of the poses of the people that it sees, the background information. For example, some cameras have more varied backgrounds, whereas others have more plain backgrounds, and that could cause a difference in the performance because of bias. So our contributions in this paper is basically to quantify, when you talk about imbalance, what do we mean? So in that sense, we try and quantify for certain queries, if they come from some cameras, what do they tend to perform better than the other cameras? And for gallery pictures from a certain camera, do they get retrieved more easily than others? So evaluation metrics, we also collected a data set with a high level of this type of imbalance, and that's part of our contribution. And finally, our method tries to address this imbalance problem, not from the data perspective, but from the bias in cameras. So the basic feature extractor is like a ResNet 50, but what we do is we split the input feature into one part that tries to encapsulate the identity information, and another part that tries to encapsulate the camera information, and these two are classified. So in doing this split and training the model, eventually we hope to just use the identity features to perform the task of re-ID. And so as a result, we tested our method by applying it on baselines. So we add our method to the baselines, and we show that for the underperforming cameras in the data set, there is an improvement. So this is what this table says. And then we also show that in the process of adding this method, we do not cause the old evaluation, which is the overall non-camera specific evaluation, we do not cause that to drop. So as you can see with the standard baseline, by adding hours, you can maintain the same level of performance or maybe do even a little bit better. So that's the summary of this work. Yeah, I'm done, I guess. Was that about 3 minutes?
Sorry? I think so. It was like.
Well, thank you for.
Thank you very much. Have a good day.
Thank you.
Thank you.
Of this value. So what means that if this speeds up or responds with the homogeneous
Of course, please let her shine. This is the time.
Okay.
I'd like you to present your work for 3 minutes, more or less, no problem.
So need
This is
to...
this is alive.
Alive?
For the participants that are online.
Okay.
No worries, you can take your time as we're explaining to anyone.
Okay. So I need to...
The mic is already on.
Okay, so I can start it. You help me or I need to...
I put it just on your up here. To this one.
Okay.
And on one pocket.
Okay.
Ah, this is not a pocket. Is there?
No, I don't have pockets. Yeah. So.
It's possible.
No.
Okay. Perfect.
Okay. So I can start anytime. Okay. Okay. Good afternoon. Welcome to my poster. The title of my work is HDR GAN. It's talk about the goal-free high dynamic range imaging with attention-guided adversarial network. Okay, this is the proposed framework. Okay, and the problem we want to manage is that if you have 3 or many multi-exposure images and you have the object motion among these images, how can you generate an HDR image without ghost artifact? So in our framework, okay, you see there are several modules. Okay, in the first module, we will do some pre-processing. We are not only handling the 3 inputs, but also 2 additional ones. We will generate 2 additional image 1. For example, H12 and H32, they are aligned intensity with S1, but aligned pose with S2. Similarly, X32 is aligned intensity with X3, but aligned pose with S2. So this file image will go to the generator, and the generator, he tried to generate a good HDR. And to ensure the quality of HDR image, we need a discriminator to do the job. He will judge whether the image is real or is a fake. In addition, we have another module called ghost detection. He will help the discriminator to only focus on those ghost area. So in this way, the discriminator will do a better job to judge whether the HDR is good enough or not. And this is the objective comparison. And the number in red means it's number 1. And the number in blue means it's number 2. And among these so many metrics, our method always have the number 1 or number 2 performance. And this is for the subjective comparison. You have 3 input images with object motion. And on the generated input, we didn't see any ghost artifact. And with after compare with ground truth, it indicates our algorithm really do the good job to produce a very good HDR image. Okay, so that is my presentation. Thank you for your attention. Okay, it's done.
Thank you very much.
You're welcome. Thank you.
Thank you. Have a good day. Hello. C'est live. C'est pour les participants au centre. Voilà.
Ok, en français, en anglais, je suppose.
En anglais, oui.
Pas de souci.
Du coup, le microphone est déjà on. Vous pouvez, comment dire, vous présenter d'abord, parce que beaucoup oublient, et c'est bon. Et voilà, vous lancez pour...
Donc j'ai pas le porter.
Voilà.
Okay. Je vous laisse. Okay, hi, my name is Nathan Eubens. I'm a PhD student at the University of Mons and Institut Polytechnique of Paris. And I'm presenting a paper called one-cycle pruning. which is based on two observations. The first one is that the pruning is usually based according to a three-stage pipeline, consisting of first training the model, and then alternating pruning and fine-tuning phases. We first find that such a schedule is very time-consuming, but also that it doesn't allow to take advantage of the regularization effect of the pruning. To overcome those two limitations, we propose the one-cycle pruning that allows to introduce sparsity along the training process and right from the start, according to such a formula. This formula has two parameters, allowing to either customize the steepness of the curve or its offset. By performing a grid search, we find that the two best values are alpha and beta being equal to 14 and 5. We perform several experimentations. The first one is by first fixing the training budget and compare to our technique to three other schedules. And we can see that for a fixed training budget, our schedule is performing better. The second experiment is the opposite. We fix the target accuracy that we want to achieve and let the network train for as long as it needs. And as you can see, the one-cycle pruning requires less and fewer iterations of training to achieve our target accuracies. And we can also see that the iterative is the most costly. That was one of the observations that we done initially. The third experiments concern the winning tickets, and we show that performing lottery ticket experiments with our schedule allow to find better lottery tickets. And the next experiment that we perform with the lottery tickets is to study their stabilities by first finding the lottery tickets and then training two versions of the found tickets and interpolating between the two found tickets. And we can see that for each sparsity levels, the LCP finds better and more stable tickets than other methods. So yeah, to conclude, we can see that the LCP, the one-cycle pruning, allows to reach higher performance than other schedules, but also faster than those schedules, but also to find tickets that are better, of better quality, and that are more stable than other methods. Thank you.
La régularisation par dictionnaire.
On est l'équipe vidéo en fait de 2022 et on aimerait bien que vous fassiez pour nous en fonction de votre travail pour avoir plus ou moins par ça. Et c'est vrai que pour les participants qui n'ont malheureusement pas pu
Je suis pas obligée de faire maintenant, parce que 3 minutes.
Non, bien sûr. Mais si c'est plus, pas de soucis.
Là, je suis plutôt sur 20 minutes que 3
non.
minutes.
Si ça peut ne pas dépasser 5 minutes, ça serait bien.
Ok, bah, j'ai besoin un peu de temps du coup pour y réfléchir.
Pas de soucis, on revient vers vous par après. Merci.
Hello.
Present your work in 3 minutes, like for participants that are online. And no worries, as if you are you can say no, but as if you are explaining to like anyone, it's not long. 5 minutes, for example, no problem. If it's just general, if you would like. We've done like this for 3 days for most participants, it would be like this, but not only guys.
I would say no, please.
As you like. Have a good day. Thank you. Hello? I think you'd like to present your work that you work for like 2 minutes, 5 minutes maximum. And it's like for participants if you would like. We've done this for 2 days, like for many participants, most of the participants would like to present. I can do that. Okay, perfect. So the mic is already on. Don't forget just to present yourself first and then start your presentation. I go through the just remember what you work and then you can start.
So the mic is on. Sorry. Oh, sorry. One problem.
Oh, okay. Thank you very much. And hello, everyone. I'm from Waseda University in Japan, and my research direction is learned image compression, which uses deep learning to solve the image compression compression task. And my topic today is to prune the network, prune the learned image compression with some pruning method. And for the preliminary, I want to introduce some of the learned image compression, which uses a encoder, a main encoder and main decoder, whose input is the image and generates the latent representation Y to be coded to strings and transferred to the decoder, and the decoder will reconstruct it. But this main codec do not perfect because there are a lot of redundancy in these latent representations. So there are hyperpaths which extract the mean and scale of the latent representation, and after that, our work is based on the hyperpath, which uses 40% parameters but only 3% calculation. And we do some experiments that we just manually prune this hyperpath from 5x5 kernel size to 3x3 and 192 channels to half of them. And there's no performance drop on this network. So we decided to use a pruning method to prune this network, which we used is called reswrap, and it uses a 1x1 conv layer after each conv and to prune this network. And after pruning, we combine this norm conv layer and this 1x1 conv layer, and it can get good performance. And our method is to apply this method to this learned image compression task, because the original reswrap has only normal conv layer, and we use pixel shuffle layer and transpose conv layer in learned image compression. So we apply this reswrap onto the pixel shuffle layer and transpose conv layer, and maybe these equations are too difficult to illustrate here, so you can understand with the paper. And after we pruning this network, we found that the performance of this pruned model do not drop, even better than the original one. But we prune at least 20% of the parameters in the whole network. So after pruning, this network can even smaller to apply to the such as edge devices or mobile devices. So this is all of my work here. Okay, thank you very much. Yeah, finished?
Thank you very
much.
Thank you.
For the ICIP process online, after watching us online.
Will it be recorded?
Yeah, it will be now live. And then we show only for the participants. You can see how they 20 minutes on average.
How long will it be? How many days? Or?
It would be like normally it's per minute after this, but in the website with the code and so the audio is already on. You can simply present yourself and then present your work.
Okay.
want to practice, please?
So this work is on adaptive compressive sampling for mid-infrared spectroscopic imaging. So spectroscopy in the mid-infrared gives us molecular information. You can get information about lipids, proteins, nucleic acids, and we can use this information, molecular information, for disease diagnosis in biomedical applications. And typically a standard instrument, which was something like an FTIR imaging instrument, collects a cube of data. You have an image, and in each pixel you have a wavelength axis, which can be 100 or 300 wavelengths in the infrared. And our goal in this project is to do adaptive sampling, meaning we have a new kind of imaging system which uses a laser scanning mechanism, where instead of it can selectively collect a subset of pixels and a set of images at different wavelengths. And the goal here is to reconstruct the 3D cube by collecting a relatively small amount of data. And so the algorithm here allows you, so you collect one wavelength image, then you use a super pixel algorithm and segment the image and collect data at these red dots, which are a small number of points. You collect spectra at these points, and you do some PCA and data processing on the spectra, and then select the next wavelength to collect data at. And then you take that image, collect the next set of spectra. So we iterate this, and at each wavelength, and you collect a few spectra and the next wavelength and the next set of spectra, and it converges very quickly. And the bottom line here is that in we can achieve a factor of 10x improvement in the data collection speed. You collect a smaller amount of data and then reconstruct using a lasso reconstruction algorithm, which is detailed in the paper. So this way you can actually do the complete reconstruction. And not only that, so typically we use RMS, or mean square error, as a measure of correctness of the reconstruction. We propose a new metric, which is classification accuracy. So these are our cancer tissue. These are different types of cancer, and we have different tissue subtypes. And we have previously we have published on how to do classification using this type of data. And we can use a trained classifier, and in after each reconstruction, look at the classification accuracy. And we can use that as an additional criterion for convergence. And after a few iterations, we see that the classification accuracy converges. And this way, you can collect a smaller subset of the data, construct the full cube, and you have classification results in an integrated manner. And so, and we show that this, by all measures, this reconstruction works quite well. Thank you.
We're currently broadcasting the presentation of the people. Would you like to present your work? So,
and also you can take me a picture because I need to set to my university.
Yes. Okay. I'll just put you the mic. Can I take the pic? It's okay for you? Yeah.
Okay, thank you. Okay, thank you to come to my poster that is titled Deep Coded Aperture Design, an End-to-End Approach for Computational Imaging Tasks. Especially in computational imaging, we have optical elements to encode the high information of the scenes. For instance, they have some about the spatial information, other from the depth, other from the angle, and there are different information of the scenes. That is when a light comes from the scenes, and we usually in the computational imaging community, we develop some optical system to encode this information in a 2D projections. So after you need to employ recovery algorithm in order to obtain the 3D information or 4D information according to the sensors. Some of these elements include an important element that is called the code aperture. So this code aperture usually is binary. It has block or unblock the light. So this is used in a lot of systems, for instance, in spectral imaging, polarization, and phase retrieval. A lot of applications include this optical element. Usually, you can employ random code aperture, but the more interesting part is that you can design it for a specific task and for a specific data set. So this is one the main worries, that you can design the code aperture for a given data set and a given task. So you can employ an end-to-end approach that consists of model the optical system, has a layer that can be coupled with a deep model that is specialized for the task, and you can train this one in simulation, and after that with the optical code aperture you can employ it in a real system, and then you can obtain some results. But first you need to train this based of some restrictions, because for instance the code aperture needs to be binary. So when you train this one, you need to say to the network that this weight need to be binary. This is the main idea of my work, that in this end-to-end approach you have a loss that is based on the task, classification, reconstruction. You can put whatever you want, but you need to say something about the behavior of the weight associated with the code aperture. For instance, the code aperture needs to be binary. You can include this regularizer in your optimization in order to obtain binary values, zeros and one. For instance, if this becomes 0, this loss function is 0 because this term, and if this 1, this becomes 0 and it is minimized. So when you train this one, based on back propagation, something like that, the loss is given for the task and for the regularizer, and the end become binary. Also, we propose a transmitter regularizer that is control the number of 1 and 0 elements. The correlation, because when you take several snapshots, you need to be uncorrelated as possible. The number of snapshots is very nice because you usually don't know how many snaps you need to take, so you can employ this one in order to get an intuition, because some of the code aperture becomes 0. That means that it's not taken based on T L2 L1 regularization, and also you can employ a different precondition that is based to work not only with the deep decoder, also with a iterative method that is very known this one. So we evaluate our proposed method in 2 optical architecture and also in 2 tasks. The first one is the single pixel camera that you employ classification, and he do an ablation study when you variate the number of regularizers. For here, this is random, yeah, we don't design, and this is if you design, you win like 10% of if you design, but even if you include, for instance, the correlation, the binary correlation mass condition, and something like that, you can improve the reconstruction of the classification accuracy. For the other side, we use the reconstruction of the cases system and also have the same performance if you use random or if you design. So this is very interesting how you win in these scenarios. And we have the opportunity to implement in a real lab. So we have the cases system where the optimal design we put here in the lab, and we show these results. That is based, for instance, if you use random, use the binary design, use the design regularizer. So from 1 to the projection, we can recover like 31 bands, and the performance you can see here in the picture is very nice with real data. Finally, also we compare if we fix and we learn the code aperture, and also this is simulation, and we win like 4 dBs. And finally, the more interesting is you can employ whatever decoder, because the decoder can be used the state-of-the-art decoder, and we propose the best code aperture for this decoder. I evaluate in HyperReckonNet and HiRC DCC network that are state-of-the-art network, and in both cases, if you design, you win. You win in the optics part. So this is my conclusion. My conclusion is that you can include regularizer in your end-to-end scheme in order to give some intuition about the network, for instance, binary, transmit, and that's it. Thank you very much. Thank you.
Thank you very much. Avec vous.
Voilà. Merci beaucoup, on reste en contact. Téléphone. Ça roule, c'est très sympa. Merci beaucoup. Passe une très bonne soirée.
C'est bon.
And at the opposite, this environment with different concepts will be far away. So to train this kind of use because of something pairs of complex research methods, the other definition of the assets probability, we would like you to present your work. If it's average, the possibilities are online, if it's possible. So we are doing this for 3 days, the last day, if you would like to present your work. Questions?
Yeah, only for 3 minutes, like a brief or more detailed as you like. You have to choose.
Yes, I can do it in.
So the mic is on. You can start by presenting yourself and then start presenting your work. Okay.
So it will be simple.
You want packets?
Nope. Nice.
Okay, so hi everyone, I'm Pierre Jacob, and I'm the first author of this work about metric learning and generating virtual examples. So in metric learning, what you want to do is to learn a structure space where visually similar images will be close to each other, and at the opposite, dissimilar images will be far away. There is a drawback of such kind of training, which is when the training going on, it is harder and harder to sample pairs or triplets that are relevant and that will give gradients for the training. So what we do usually is to do some mining to find which pairs or triplets are relevant for the training. But it costs a lot, and what people do more recently is to do some example generation. So you are synthesizing new examples from the real one. And most of the drawbacks that you have for this kind of method are they are either too hard if you use some kind of adversarial network, which means that you might generate them outside the class manifold and they will completely destroy your space and you have to redo everything. Or at the opposite, they will be too easy, for instance, by using variational approaches and so on. So the idea of the paper is to use what we call virtual classes. So you are basically learning new classes that are only composed of virtual examples that you will generate, such that they will not destroy your embedding space. So when you are optimizing your network, even with a wrongly labeled example, this one will be pushed back to its class, so it's fine. And you are only modifying the shape of your virtual manifold, which will only impact the weights from your generator and not destroying your learned space. So how can we sample such examples from these virtual classes? So the idea is inspired by variational generation. So instead of using directly the mean of your training classes, we are running some prototypes
such that they will serve as seeds to generate new examples. So given a prototype for a class, you will generate as many examples that you want from this given class. And you do your training using your constancy, blood triplet loss, or whatever metric learning loss that you prefer. So does it work in practice? So the answer is yes, of course. And it's very easy to train because you are only slightly modifying your examples from this prototype. So so your generator and your discriminator will be very small network with like 2 or 3 layers. So it doesn't cost a lot. It's very easy to train because at this point of the training, the space is already well structured. So it's very easy to initialize your adversarial network. And in practice, we observe that even in very high dimension, you have your examples or your virtual classes that are very close to training examples. And in practice, it's more of 80% of the time. In terms of generalization performances, there is a nice improvement compared to the baseline. And what we observed is that you don't really have to tune the parameters. So for instance, if we only look at how many training examples we need for the training, we observe that if you put a lot, it doesn't hurt the training. So in practice, yeah, just put as much as you can to fill the batches. And regarding the virtual classes, we have the same observation. Even with a very large number, it doesn't hurt the training process. Thanks for your attention.
How much time will I have? 3 minutes?
4 minutes break. Make sure the mic is on.
We are not playing kernel.
It's good. Hello, my name is Devashish Lohani, and I'm a PhD student in University Lyon. And here I present you my work on unsupervised and parameter intrusion detector. So what is our problem? The problem is to detect intrusions in the video. So here you can see an intrusion is an object which is unauthorized and it is moving in a parameter that is protected. So here, as you can see in examples, there is humans, for example, is unauthorized in red, and they are in the protected parameter. So these all are intrusions. But for example, there is an insect which is moving. It doesn't belong to the unauthorized category, so it's not an intrusion. So in the state of the art, there are works which use handcrafted rules for this, or they use some external data set or external network like YOLO network, but they're not too robust to the scene dynamics. And we propose an unsupervised approach. So basically our approach is to learn normality from when we train. So basically we propose a 3D convolutional autoencoder. This autoencoder takes 8 images as a small volume, and this volume is reconstructed from the autoencoder. And this reconstruction and the input is the mean square error is calculated and it is minimized, it is backpropagated so that this network learns what is normality. And during the testing phase, this when we have intrusions, the autoencoder is not able to reconstruct these intrusions, so we can calculate the error, and this error helps in detecting the anomalies. So for example, here you can see the reconstruction error, and as you can see that this reconstruction error, it evolves with time. So during the day or during the night, you cannot have the same reconstruction errors, Therefore, it is very difficult to choose a threshold to to detect anomalies. That is why we propose an adaptive thresholding method. So here we propose a moving z-score which adapts itself with time. So here you can see at the end of the image that it adapts itself with the time, and we are able to detect the beginning of each intrusion event. And here you can see the quantitative results, that when we use our adaptive threshold strategy, we almost double our results. And finally, we compare with the supervised method that use YOLO network. And as you can see, we outperform other methods in all the existing data sets of elites. And that's it from my side. Thank you.
In the talk, but actually I never used it or have seen the formula.
Okay. Okay, sure. I mean, so
yeah, of course. There was a mic here. I want to be too loud.
Excuse me. Is this video recording mandatory?
No. If you would like, we can pass you now. Be good. Yeah, I have a time. In the one that is the last.
We're broadcasting the presentation of the people. Where do you have
You can continue.
So we want to compare the estimation that sample that we have here with the sample that we have distributed. And our paper is that this sample is dark enough to allow for the meaningful comparison. So it would be hard for me as a person to tell whether.
Hi, my name is Yoshihito from Hitachi Limited, Japan. I will explain about my paper titled Efficient and Accurate Skeleton-Based Two-Person Interaction Recognition using Inter- and Intrabody Graphs. Human action recognition has been widely applied to many tasks, such as video surveillance. Skeleton-based two-person interaction recognition, such as talking or giving an object, have been gaining increasing attention as advancements are made in pose estimation and graph convolution networks. GCN-based human action recognition methods, predefined considering physical connection like wrist to elbow of human body, have been explored over the past few years. However, it can still be improved in two aspects: computational cost and accuracy. It is difficult to balance low computational cost and high accuracy. Okay, the contribution of this paper is that our proposed method achieves the highest accuracy and low computational cost compared with the sorted methods. Here is the overall architecture of our proposed method. Our model consists of three kinds of streams: intrabody stream, first and second interbody stream. Each stream has one or more branches to process joint coordinates, their velocity, and bone information. Bone information is that vector between adjacent joints on a predefined graph. And in each stream, spatial graph convolution, temporal graph convolution, and attention layers are iteratively performed. We introduced three techniques for reducing computational cost and two techniques for improving accuracy. First technique is aggregation of branches. There are 6 branches in total. These branches are aggregated into 3 streams by the same input shape and predefined graph type. Second and third technique is actually off-the-shelf technique, factorized convolution and model scaling strategy, which is introduced in MobileNet V2 and EfficientNet. To improve accuracy, first technique is the collaborative use of intra-body graph and inter-body graph. Intra-body graph is originally introduced in FTGCN, but it is inappropriate to utilize it only for human interaction recognition task. So we proposed distinctive graph representation as inter-body graph, and we utilized it together to capture the relationship between two bodies by graph convolution. Second technique is inputs into branches. As I mentioned, three kinds of features are utilized in our methods, and especially inputs to B2 branch. Here are relative distances between persons, joint, and the other person's 6 representative joints, head, torso, distal portion of extremities. Okay, let's move on to the experiments. We evaluated our proposed method through the experiments using large-scale human action recognition dataset named NTU RGB positive 60 and 120 that contains 11 and 26 classes. Here, we evaluated our proposed method with state-of-the-art methods. As shown in this table, our method shows the highest accuracy in all of the validations, even with the smallest Bezo model achieving an average improvement of 2.3% in NTU 120 dataset compared with SOTA method. And the Bezo model has only less than 1 million parameters. And the inference speed is 5 milliseconds per sample using the RTX 3090 GPU. Yeah. So therefore, it is important to utilize interbody graph and relative distance features for accurate human interaction recognition. Thank you for listening. That's all my presentation. Thank you.
Looks like you were up for
It's Dan Boss. Is it required? No. But it's good visibility. I wish. Present your work. Yeah, sure. It's yeah, it's no problem. Go ahead and mic me.
Take care of the mic is on.
I have this but if I use the score, I almost double my percentage.
Hi, I'm Ryan Webster. I'm a PhD student at the University of Caen Normandy in France. In this work, we looked at training a GAN on multiple data sets at once. Typically right now, GANs can only train on one specific data set. And there's also several methods which can adapt a trained GAN and transfer it to a new data set. So we really looked at, in this work, how should you share parameters for a GAN trained on multiple data sets at once. We explored several ways to share the parameters. Our main contribution was a relatively simple observation that there's a new way to share parameters which is much more effective at transferring knowledge from a source generator to a target generator and also training at multiple data sets at once. So methods thus far are training by layer. So there's one method, MindGAN, which will train the input layer of a GAN network. So we summarize the methods that train by layer in the left here. The blocks in red here are layers that are retrained. So methods such as MindGAN and StarGAN train entire layers at once or not. And then our new method, which to our knowledge is not in the literature yet, is going to each layer and then slicing that layer and retraining some parameters in that layer or not. So before we began our experiments, we just investigated what happens when you corrupt or change parameters in either one of these sets. What we wanted to look at is how does changing certain parameters affect the generation quality of StyleGAN2? So what we did is we wanted to corrupt a certain amount of parameters. So in this case, I think we corrupted 1%. We go to the StyleGAN network. We either corrupt layer-wise, so we go to the input layers of the network because that's what StarGAN and MindGAN are doing, and we randomly corrupt parameters. And we get something on the left here, which shows that the image quality is greatly degraded. But if you degrade parameters sort of equally across the entire network, then you kind of preserve the image generation quality. So our sort of conclusion from this is parameters within each layer should be redundant, and some of them can be repurposed and retrained. So this was our primary insight, that we should have a budget that exists across the entire generator. So we first did a transfer learning experiment where we start with a source generator and then train on a new data set. And when we do this, we either do it layer-wise or width-wise. We show that width-wise sharing is both more efficient, so given a particular budget, it's better at transferring to new tasks, and can do harder tasks. So in this case, we transferred from faces to churches, and our method can handle this case, but if you do it layer-wise, it doesn't handle this case. And then finally, we move on to sharing during the training procedure. And we also show that for this, our width-wise sharing procedure outperforms StarGAN v2 when you have multiple highly different data sets. So sort of the TLDR is this trick here for sharing works well in the image generation problem. Hasn't been done before in the literature. Can do both transfer learning and learn multiple domains at once efficiently and create good shared representations. We also provided a little bit of insight in how parameters affect generation in the StyleGAN network.
Thank you very much. Great.